Let's now look at how we can actually use electric potential to solve some quantitative problems. And I'm going to briefly go through the problem-solving strategy and then do one problem that isn't necessarily quantitative itself, but it's going to show you conceptually how to begin these. And the rest of this chapter really looks at specific situations, so I encourage you to come back to this after you've seen more about electric potential. So the first steps is going to be modeling and simplification. And so in general, one of the models we're using is the energy model, and that means we're going to want to think about an isolated system and we want mechanical energy to be conserved. So this is going to be true as long as there's not an outside force and there's no drag or friction forces. So that is a modeling step or a simplification step. Other simplifications you're going to want to use is looking at your system and simplifying it by expressing it in terms of simple objects. So for instance, defining things to be point charges, modeling things as infinite planes, as infinite wires. So that's going to be a big part of simplification, is looking at real-world objects and expressing them in terms of shapes you know how to calculate. Visualization here, you're going to usually want to do a before and after. Why? Because inherently we're talking about energy here, right? This is conservation of energy in charge interactions. So anytime you have conservation of energy, you want to do a before and after so that what you mean by final and what you mean by initial is really clear. So on those pictures, you want to actually define your symbols, list your variables, label as much as possible, maybe draw a coordinate system. So then the solving, we start with this conservation of energy equation and note that Q times V is just the same thing as talking about potential, U. But frequently we're going to actually be using electric potential, not just directly potential energy. So that's one reason why it's expressed this way. So you start from here and then you're going to work towards whatever it is you're asked to solve. So let's look a little more at solving. So we're starting from a good expression of conservation of energy, and then we have to think about what each of these terms mean. So is electric potential given? If not, you're going to need to calculate it. And again, this is going to be something that we're going to look at in future videos. How do you calculate the electric potential from, for instance, a disk of charge? Well, you know how to do that, so if it's a disk, that's how you figure out what these V's are. The next thing is that whenever you have kinetic energy, now we're frequently going to have multiple moving objects. Maybe not, but make sure that you sum everything up. That if you have 2 point charges that are both moving, both of their kinetic energies need to appear here. You can't just use the kinetic energy of one particle. You might use additional conservation laws, such as conservation of charge. Remember that charge can't be created or destroyed. We can separate a neutral object into being polarized, having positive and negative charge. We can transfer charge from one object to another, but we never just make positive charge appear out of nothing. Sometimes we're going to have conservation of momentum, and remember that your system momentum initially is equal to your system momentum at the end. P initial equals P final, and I use capital P here to show that you must consider the momentum of every single piece, and these are vectors. So again, go back and look at some Physics 202 videos if you think you need to use conservation of momentum and don't remember anything about it. In the end, you should always check that your result has the correct units, significant figures, and look and see if directions make sense. If you've said that an object is speeding up, do you actually think that your kinetic energy is larger there? So always do a little bit of a quick check. So now let's do a little bit of a conceptual example, since this is important to understand how we're going to move into quantitative problems. The example is this. We have this representation here of potential, which is going to be equipotential lines, and we're going to meet these very soon. If we start with a proton at rest at B, what is going to happen? And so we say that we have Ki equals 0 here because we say that it's starting at rest, right? So we know that lowercase v, our velocity or speed, is initially equal to 0. Well, you have to be a little bit careful in these problems, and that's why I picked this. If you just say, well, hey, my potential energy is going to equal my charge, and in this case it's of a proton, times my initial potential, and I see that my initial potential is equal to 0, well, then if you say it just stays here, nothing happens, that's not actually right. So we discussed in a previous video the idea that potential energy can be negative, and that's the same case here. Note that we have a negative potential here and a positive potential here. Again, we will talk in a future video about how these sorts of representations relate to electric field and how you can interpret them. But what this actually corresponds to is a uniform electric field pointing to the left. So we have a uniform field to the left, which means a proton, you know, is going to experience a force to the left. And if you notice, this is more negative. So if we call this, and I'm trying to use capital V here to distinguish between speed and potential, my final potential here, at point A, I get to say that my K final plus my final potential energy, which is just Q, times V final, again capital for the sake of clear notation, equals those initial ones, and this was in fact 0. So we get to say that that whole thing sums to 0. But now this term, right, notice that this is negative and Q is positive. This is in fact less than 0, which allows my final kinetic energy to be greater than 0, which means it's moving. So if we start our proton from rest here, it's going to start moving to the left, speeding up, gaining potential energy as gaining kinetic energy, I misspoke, as our potential energy decreases, because we see that our electric potential decreases. So we'll spend more time with these types of representations and thinking through this, but again, it's really important to be able to go from electric potential to potential energy, and remember that that can be negative.